Welcome back, students. We are finally going to apply all of the things we've been talking about in quantum mechanics to an actual problem that is relevant for chemistry. And we'll do that in this chapter by looking at quantum mechanical models for the vibration and rotation of molecules. So the vibrational modes are simpler, and we'll start with those, and we'll pick up with rotational motion next time. All right, so we'll start here with vibration, and to do that, we'll evaluate the model known as the quantum mechanical harmonic oscillator. The learning goals for this section are going to be to solve the Schrodinger equation for the harmonic oscillator. You'll see what I mean with the quotes there. And then we're going to want to be able to compare this with our particle in the box. So this type of motion is going to be much more complicated than translation that we saw in the particle in the box. But we can still compare and get a lot of information out by just evaluating it in the same way we did with the particle in the box. We'll get the wave functions at the end, and we'll want to be able to be comfortable with using them and solving problems with them, as it's going to be important when we want to evaluate these modes in spectroscopy. So with the particle in the box model, we looked specifically at the translational energies of particles. So the particle is moving around in the box, that's corresponding to translation. And we saw that if we did not put the particle in a small box, the translational energy levels were essentially continuous. They were the differences were so small that it was continuous. What we'll do today is look at the vibrational energy of molecules. And then next time we'll look at the rotational energy of molecules. For vibration, we can't consider molecules as single atoms, because if you just have a single atom, there's nothing to vibrate. You need at least two things for the difference of those to be called vibration. So we'll consider the way that the molecules can take up energy, right? We talk about translation, vibration, rotation. We'll talk about that more next semester when we think about heat capacity, and we can see that these quantum mechanical ideas that we're developing now are actually important for the way that molecules can take up energy. And what we'll do today, though, is look at vibration. We'll start by considering classical vibration and then extend it, of course, to quantum mechanics using Schrodinger's equation. So the classical model for vibration can be considered as two masses connected by a spring. And as the masses vibrate, they move with respect to each other. Now, this problem is kind of cumbersome. We have two different masses. We have the center of mass as the one position that doesn't move, and each of these masses will move to some or lesser or greater extent away from the center of mass. So what we do to make this problem simpler and easier to analyze is convert to what we call center of mass coordinates. So by doing this, we convert a problem of two moving masses connected by a spring to one moving mass connected to an immovable wall, is the simplification that we do. And what we're going to use the most, you can, of course, find the coordinates of the location of the center of mass. And you can also find the new mass. And this is going to be important. So we'll see in the Schrodinger equation that when we consider molecules, we replace the m in the Schrodinger equation with this mu that's known as the reduced mass. And the reduced mass here is the product of the two masses that are vibrating divided by the sum of the two masses. And so this is something to keep in mind as we go and solve problems using things like vibration and rotation. This center of mass coordinates is going to be important. So now that we have this, we can think of, how springs work. So what springs do in these vibrators, what they're going to do is they're going to displace from an equilibrium position. And here, again, in this example, we have two displacements for each mass, but if we convert to a center of mass coordinates, we just have one displacement. So we'll have one variable x, and x is going to be the deviation from the equilibrium position. If x is positive, it's further out than the equilibrium position. A negative x would be more compacted from the equilibrium position. And of course, with the spring, this will both of these will happen as the molecules vibrate, as the harmonic oscillators vibrate. There is a force, and that force opposes the motion. So the force that we'll see is as follows. So the harmonic oscillator can be seen like this. We have a force, and we have force, which is equal to mu, again, mu being the mass, times the acceleration. The acceleration is, of course, equal to two derivatives with respect to time. We remember this from physics. So this is the kinetic energy, the forces that they're talking about, how these particles are vibrating. There's also a potential energy that resists this motion that's stored in the spring. The negative sign indicates to us that it opposes the motion. And then there's K, the spring constant. The larger the K, the stiffer the spring is. And then X is the distance. So we can see here for the classical harmonic oscillator, we have a differential equation. We have two derivatives of X with respect to time, and we have a negative constant times X. And we're pretty familiar with this. We know by now that the solution for this is some sum of trigonometric functions. And if you have, or if you will at some point go on to take a differential equations class, you'll work with this example a lot. This is one of the classic examples for solving differential equations. And just like in normal physics, we have V1 and V2 that are going to set the initial conditions, and we can call those in quantum mechanics, we would call those the boundary conditions. And so this function here is going to be used to describe the motion of a vibrating system, right? A spring in classical physics. And again, like we've seen before, since we're treating this vibration here under classical physics, we don't see any quantization. All energies and positions are allowed for the classical harmonic oscillator. Now, how do we take this problem and apply it to the molecular bond? We can see that at some level, bonds are similar to our harmonic oscillators, right? So if we stretch bonds, they're going to resist that stretching from equilibrium distance. If we compress them, they're going to resist that as well. But the way in which they do so is going to be a little bit different than the harmonic oscillator. So it turns out that this is actually a pretty good approximation using this simple motion of harmonic oscillators. And at the end of the lecture today, we'll look and compare to maybe a more real understanding of how bonds work, and talk about, when do we want to use functions that are more accurate than the harmonic oscillator. So the first thing that we need to do is set up the Schrodinger equation if we want to apply this to the molecular bonds. And so we can do that. And of course, what we need to know is the dimensions. Again, we only have one type of dimension. We just have the position, the displacement from equilibrium. And now we need to know the potential. So the potential energy in this case is the spring potential energy. So the potential energy for a spring is simply 1/2 kx squared. So we showed before that the force of the spring was kx, and integrating that gives us 1/2 kx squared for the potential energy. So we have this function, and all we need to do to figure out what wave functions and energies are allowed for quantum mechanical vibration is to solve this equation. Now, you may have noticed that this equation is much harder than the equations we were working with the particle in the box model. In this case, we have a potential, and it's not constant, it's x dependent. So now what we need to do is take two derivatives of our function, multiply that by negative h bar over 2 times the reduced mass, and then add our function times 1/2 kx squared, and return our function multiplied only by a constant. So this is pretty hard, and the solutions for these are not obviously going to fall out of our basic understanding of calculus like they did for the particle in the box. However, these solutions were already known at the time when this quantum mechanical model for vibration was described. These have been known by mathematicians for centuries before. And the solutions are as follows. So I'm going to walk you through what this means, and we'll see some examples of these solutions. So our psi of n here, of course, n is our quantum number. The allowable indices for the quantum number vary by the problem. In the case of quantum mechanical vibration and the harmonic oscillator, the n starts at 0. So 0 is allowed, and then followed by integer numbers of 1, 2, 3. The reason for this isn't super important. It has to do with the boundary conditions and solving the problem, and that's a little bit more complex math than we want to be able to do. So just know that for vibration, n starts at 0 and increases in integer steps of 1. So the functions here that are solutions to these equations, first we have this a sub n. In this a sub n, we can see this down here. It is simply a normalization constant. So it's 1 over 2 raised to the n times n factorial, take the square root of that, and then take alpha over pi to the 1/4. So this is all constant here. Alpha is based off of our parameter, so it's based off of K, the spring constant of the bond, the reduced mass of the two atoms, and then Planck's constant. So our A sub n is simply a normalization constant. Remember, I told you before that all of our wave functions typically come normalized. So here this A constant normalizes our wave function. So the integral of the square of the magnitude of these wave functions will be 1. This next section is the Hermite polynomials, and that encompasses this whole section. So these h sub n's are polynomials, and they're polynomial functions of the square root of alpha times x. So this is not hn times the square root of alpha times x. This is hn as a function of the square root of alpha times x. And here we can see, again, these are just a series of polynomials. They come from this equation here. I don't expect you to work with this. I just show it because I am interested in this kind of stuff. So I figure some students may also be interested in this kind of stuff. So if you take, 4 derivatives of e to the negative x squared and then multiply it by e to the x squared, you come up with this polynomial, and that is the first of the Hermite polynomials. And so to evaluate this in terms of the wave function, we would plug in alpha, the square root of alpha x for every instance of x squared. That's what it means to have h4 as a function of the square root of alpha times x. The last part is this Gaussian function, e to the minus alpha x squared over 2. And so putting all of these pieces together, the normalization constant, the polynomial, and the Gaussian function, we get the wave functions for the quantum mechanical harmonic oscillator. Just like before, we can do things like verify that these functions are solutions to this equation. So if you take any one of our functions, I'll show them here. Here's the first 4. We can take these and evaluate them and return the energy, right? So if we were to take this equation, plug it in here, we would find a single constant multiplied by our original function, and that constant would be the eigenvalue, and that is the energy. So now, of course, we can evaluate the energy. We can plug in these various equations, and every time we plug in an equation, we'll get a constant, and that multiplied by the function, and that constant will be our energy. So if we do that, we evaluate our wave functions here with the Hamiltonian, and we get the following. So for psi of 0, we get h bar over 2 times the square root of k over mu. For n equals 1, we get 3/2 h bar times the square root of k over mu. Then we get 5/2 h bar times the square root of k over mu, and it would continue. So with this, we can get an expression for the energy as a function of n, and that is as follows. So the energy is equal to h bar times the square root of k over mu times n, the quantum number, plus 1/2. Again, here we see 0 point energy. There's always energy associated with this, even if n is equal to 0. And I want to familiarize you with this as well. This is the more common way that we'll see this. So you can see that the n plus 1/2 is the same. And here we've substituted hc nu with this squiggle over it for h times the square root of k over mu. So this is a more common way of evaluating this because it's a little bit simpler and more easy to see spectroscopically. So here, the nu with the squiggle over it is our frequency of this vibration in terms of wave numbers or inverse centimeters. And then all we have to do to find the energy of that is multiply by Planck's constant times the speed of light in centimeters, and that will give us an energy in terms of joules. So since spectroscopy typically works in inverse centimeters, we'll see it in this form more often. Here we'd have to go do and calculate things like the force constant of the bond and the reduced mass. Both of these are built into this frequency constant here. So we'll more often see it in terms of this, but of course we could convert it at any time if we looked up things like the reduced mass and the force constant. So here we can see that unlike the particle in the box, the energy levels for the harmonic oscillator are evenly spaced. So as n increases by 1, the distance increases by hc nu. And that doesn't change as n gets larger and larger. So 2 is just as far away from 1 as 1 is from 0. Now this is very different from the particle in the box, and it's different from all of our other models as well. So the difference is the spacings of the energy levels changes, of course, as the problem changes. Now, the next thing we want to address is what do we think these wave functions might look like? They're pretty complicated. We have polynomials multiplied by Gaussian functions, and probably off the top of your head, you don't really know what those functions look like. But it turns out that these functions actually look a whole lot like we would expect them to. So our potential here, our 1/2 kx squared potential well, we can treat that like a box, an infinitely deep box. Now the sides aren't perfectly linear, and so we get these weird shapes, but the trend is the same. So we see functions that look a whole lot like half of a sine curve, 1 sine curve, 1.5 sine curves, 2 sine curves, and so on. And of course, we see, just like for the particle in the finite depth box, there's some spillover here. So there's particle density existing in this region where we classically don't think the particle is in. Now, what you cannot quite see with this image, but we'll do one more where you can see this, is that the particle is more likely to be at this extended length. So if I were to draw a line here, as even as I can, we can see that this middle peak is not quite at the same height as one of these end peaks. And what does that mean for us? It means that in this case, the particles are more likely to be at this extended length, right, at the longer lengths than at, or the shorter lengths, right, because x is displacement from equilibrium here, than at the middle. Now, does that make sense according to the classical picture? So here again, so here we'll show the probability. So again, this is just a square, and here it's a little bit easier to see where we have much higher likelihood of being at the end than in the middle. Here's another one where it's much more blown out. Now, classically, we would, of course, expect the spring to be at its longer positions rather than at this x equals 0. Now, why is that the case? Well, where does the spring spend most of its time? And at this equilibrium distance, right in the middle at x equals 0, the spring is moving the fastest as it extends and stretches. It's moving the fastest in the middle. So it's going to spend the least time at an equilibrium bond length of 0. But when it gets to the most compact or the most stretched locations, it's slowing down, and all of the energy is now potential energy and none of it's kinetic. And so we have, it spends much more time at these elongated or compacted positions. And so these wave functions, again, in the classical picture, if we were to extend this out to higher energy levels, we would, of course, see the same thing that we would expect. So now I want to make you recall one thing, and this is something that you probably encountered in math, but it's been a while since you thought about it, and that is the idea of even and odd functions. Even and odd functions are going to come in handy when we start trying to treat these harmonic oscillators in respect to spectroscopy, and we're going to use the properties of even and odd functions to make these things easier for ourselves. And that's because the harmonic oscillator solutions are either even or odd functions. So an even function has the property that when you take the negative of a number, that's equal to the same as the function evaluated on the positive number. And another way to look at these is that they are functions that are symmetrical about the y-axis. And so we can think of some examples of these functions. And so some examples would be things like x squared, cosine of x. These are even functions. And they have the handy property, since they're symmetrical about the y-axis, that if you wanted to integrate them from negative infinity to infinity, that's equal to 2 times the integral from 0 to infinity, because the negative half has the exact same area under the curve as the positive half. Odd functions, on the other hand, have the following property. If you were to take the plug in negative x to that function, they give negative the value that happens when you get positive x in that function. So some functions that are positive are not a positive. Some functions that are odd are sine of x and x. And for these polynomials, right, any even x to the even number is going to be an even function, and any x to the odd number is going to be an odd function. And odd functions are reflected across the x and y axes. So that means that any area under the curve from negative infinity to 0 is the exact same in magnitude and opposite of sign as 0 to positive infinity. So the integral from negative infinity to infinity of all odd functions is 0. And these two properties are going to help us out. Now, even and odd functions work just like even and odd numbers, where if you add two odd numbers, you get an even number, and if you add an even and an odd number, you get an odd number. So the product of two even functions is an even function. The product of two odd functions is an even function, and the product of an even and an odd function is an odd function. So for example, we can go in here, look at our psi of 0. We have a constant times an even function, so this is an even function. Here for psi 1, we have a Gaussian, which is an even function, times x, which is an odd function, for an odd function. And then here we have this quadratic, which is an even function, Gaussian even function, so psi 2 is an even function. Here we have this cubic and an x, which is odd, times a function that's even. So we can see that our wave functions alternate as even, odd, in correspondence to their quantum number. So keep these properties of even and odd functions in the back of your mind. They are going to come into play when we try to evaluate what happens to these functions when we excite them. So if we excited a harmonic oscillator, what wavelengths of light is it going to absorb? What energy levels are possible? And we'll see this as we get into next week. So keep these ideas in the back of your mind. Lastly, I want to visit the idea that bonds are not quite like harmonic oscillators. So of course, if I were to ask you to draw a picture of the potential energy well of a molecule, hopefully you would know what I mean. And if you don't right now, you'll know when we talk about this in class. And you would draw something that does not look like a harmonic oscillator, because at infinite distances, our molecule will dissociate. So unlike a spring, I could actually pull two atoms apart. I would break the bond, and then they don't interact with each other anymore. And so our actual potential looks more like this in red. So this is called a Morse potential that describes anharmonic oscillation. And for the anharmonic oscillator, there's a much more complicated potential energy, and then an energy as a function of n that has the same base energy with this extra term here to account for the anharmonic oscillation. And so what we'll see is that the harmonic oscillator model works very well as long as you're dealing with things like n equals 0 and n equals 1. Much beyond n equals 1, the quantum mechanical harmonic oscillator stops working very well as a model. We need to consider this anharmonic potential. So, and we'll see as we go forward that if we were to use the Gaussian distribution on most molecules to see where their vibrations is, almost all vibrational modes for molecules are almost exclusively in the ground state. So when they're excited, they'll go to the first excited state, and it works pretty well to use the harmonic oscillator as a model. Now, for some molecules, particularly molecules with very large atoms, that is not the case, and more levels are accessed. And then we get out of this very bottom of this well here into this kind of region where our prediction then becomes worse. And ultimately, you can see here that our harmonic oscillator model predicts that it keeps getting harder and harder and harder to stretch these things apart, wherein, of course, we know at some point the bond will actually break and it stops getting harder to stretch them apart. So at things like high temperature or for heavy atoms, when the distance is long, more accurate Morse potentials must be used. So that's all I want to say for now about quantum mechanical vibration. Next time we'll look at rotation, and then we'll put these two things together to talk about rho vibrational spectroscopy in the following week. So with that, I'll let you go and look forward to seeing you in class.